Most people are familiar with the concept of air pressure in a car tire. A flat tire is soft and low in pressure. Once any leaks are fixed, it must be reinflated to the proper pressure. Adding air to the tire increases the number of air molecules in the tire, which are free to move around and collide with themselves and with the tire's inner surface. These collisions allow the air molecules to exert a force everywhere against the inside of the tire wall. The pressure exerted by the air, or any fluid, is defined as the magnitude of the force acting perpendicularly to a surface divided by the area of that surface. The SI unit of pressure is the Newton per square meter, which is referred to as a Pascal. A pressure of 1 Pascal is a very small pressure when you consider it's equal to 1 Newton of force, about the size needed to push a doorbell, distributed over an area of 1 square meter. Many common situations involve pressures of approximately 10 to the 5th pascals, which is an amount referred to as 1 bar of pressure. Alternatively, force can be measured in pounds and area in square inches, giving another common unit of pressure of pounds per square inch, or psi. Because of its pressure, the air applies a force to any surface with which it's in contact. Suppose a small cube was placed inside the tire. As the figure shows, the air pressure causes a force to act perpendicular to every face of the cube. In a similar fashion, water applies a force perpendicular to each surface of a submerged object, like a swimmer in a pool, for example. In general, a static fluid cannot produce a force parallel to a surface. If it did, the surface would apply an equal and opposite force to the fluid in accordance with Newton's third law. In response, the fluid would flow and no longer be static. While the pressure in a fluid generates a force, which is a vector quantity, pressure itself is not a vector. In the definition of pressure, P equals F over A, the symbol F refers only to the magnitude of the force, so the pressure has no directional characteristic. The force generated by a static fluid is always perpendicular to the surface in contact with the fluid. As a final note in this section, we discuss the fluid in which we all live, the Earth's atmosphere. The air around the Earth is held near its surface due to Earth's gravity. This fluid applies a pressure to every object on Earth, just like the water in a swimming pool does to submerged objects. At sea level, the pressure due to the Earth's atmosphere is 1.013 times 10 to the 5th pascals, or 1 atmosphere of pressure. This is equivalent to 14.7 pounds per square inch, or 14.7 psi. This means that every object on the Earth at sea level, including you and me, has 14.7 pounds of force applied to every square inch of surface area of our bodies due to the atmospheric air pressure. We don't notice the air pressure because we evolved, were born, and live in an environment that is constantly at 1 atmosphere of pressure. If you were to take the air pressure away, like the environment astronauts encounter in space at high altitudes above the Earth, you would immediately experience very negative physiological effects. The lack of air with oxygen we need to survive would be absent, which might allow 1 to 2 minutes of consciousness if you held your breath. But the lack of air pressure against your body would cause the gases in your lungs to expand. If not expelled, your lungs can rupture. After 10 to 15 seconds, your skin and other tissues would begin to swell, and you might even be able to feel bubbles on your tongue as the water on it boils away in the absence of air pressure. Experiments and accidents have shown that humans can fully recover after short exposures to vacuum. Clearly, however, to live and work in space, protective equipment will be required. Astronauts working outside of their spacecraft, or the International Space Station, wear suits that provide the required pressure, oxygen, and temperature regulation for human beings.